Hello students, today we are going to learn resolving power of microscope. So in the previous lecture when Rayleigh's criterion we are discussing, at that time we discussed the ability of an optical instrument to produce distance images of two very closed objects is called resolving power. So, if the microscope is taken, then what is the resolving power of microscope? So, it is the power of that microscope to separate those two objects from each other. So, first of all, we will define what is resolving power of microscope, and then we will write the derivation for it. So first of all we will see here resolving power. I will define resolving power of a microscope is defined as the reciprocal of the minimum distance of separation between two point objects for which they are just resolved by the microscope. So this is the definition of resolving power of microscope. So resolving power of microscope is defined as the reciprocal of minimum distance of separation between two point objects for which they are just resolved by the microscope. So for this case we should know how to do this. Two small objects we are taking for our convenience, and here let us consider two objects. Here suppose I am taking two objects for our convenience. I am taking here. Let us consider these two. This is the first object I am taking as O1, and very near to it the second object I am taking, that is O2. Okay, they are separated by the distance A. This is the distance of separation. Now as we know, the microscope has the objective here, so that lens I am drawing. This is the objective of the microscope. So now first of all we will see here the first object. From that the rays are coming, and at the center it should be. So we'll draw this. Will show at the center these two lines are coming. So now here again I am taking the point somewhere here, I'll draw so that this is the middle point you should get. Now two rays I am showing here. The extreme point we are showing here on the aperture of the objective. This is objective. Okay, so AB is the objective, we can say. Now these two lines, when they pass to these two rays, when they pass through it, they will meet here, suppose. Okay, so we'll get one source image of this source objective OI1 is the image we are getting. Now from this another point we will draw, and suppose here it is going somewhere here from the center of this, and it will reach here somewhere at this point. Okay, so here again I am trying to draw this which are meeting at this extreme point, and here the another ray I am drawing. So these will be the rays which are coming from the second object O2. Okay, after passing through the objective, those will meet here, and now the diffraction pattern will be here from these two objective we are getting. And suppose here, due to this, I'll draw the diffraction pattern here. Suppose I am drawing, so this is the maximum intensity, and the bright point is occurring here. So another bright point we will show here with this color, and at this minimum intensity of this is the minimum intensity of this, and this is another point we are getting here, and we can see here the images, that is I2 and I1. So here it will be the point, and this is the another point we are getting. So now you can see here, this is the angle which is made by the two objects with the objective, that is 2 alpha. Okay, this is the first line, straight line which is going here, and this is again the straight line which is going from the object O2. So the angle between these two is 2 alpha. Okay, this much distance we consider, that is A. Okay, now suppose this is the medium having refractive index mu, or sometimes it is equals to n. Okay, so this is the refractive index of the medium which is between the object and the objective. Okay, so now here this is the diagram. Now we can show here this 2 alpha is the angular separation of the object at objective. Okay, and A will be the distance between two objects, okay, and mu, or that is equals to n, also sometimes it is taken n, It is a refractive index. Okay, a refractive index of the medium between object and object and object. Okay, so here this is the medium, and we are taking the refractive index of that medium as nu. Okay, so now we'll go next and we'll see here how to find the refractive index and what is the part difference and all. So now we'll go ahead and see here. The background will take here this type of background. So now the distance between two objects, it is given as A is what? The distance between two objects. Okay, and it is given as lambda, that is the wavelength, and numerator aperture. So it is now here aperture, that is equals to that is also given as a 2 mu sine alpha. Okay, and 2 mu sine alpha is nothing but numerical aperture of this aperture, and it is given by 2 mu sine alpha. Okay, now let us consider here this thing. There are two cases. Okay, while studying this microscope, there are two cases. So which are those cases? Case 1 is if these points are non-luminous point objects. Okay, so any object if you are taking and if you are observing those objects from the microscope, and if they are not self-luminous, okay, so we can say the case is resolving power of microscope with two non-luminous object. If they are dark point, we can say if they are dark point. So at that time, what should be the resolving power that we are going to consider? So here, first of all, we will see here A is the distance between two, and that is given by lambda upon 2 mu sine alpha. Okay, so it is equals to lambda upon 2 into what is this thing? This is nothing but the numerical aperture. Okay, in this way we can find the distance between two objects. Okay, now here if we are taking as we know from the definition, what is the definition of resolving power? Resolving power of microscope is the reciprocal of A. A is the distance. Okay, just in the previous slide we saw resolving power of the microscope is defined as the reciprocal of the minimum distance. Minimum distance is considered as A. So of separation between 2 points object for which they are just resolved by the microscope. So from definition we can write here now. This is equals to resolving power, it is given by RP of microscope. Okay, and that is equals to now one reciprocal of this minimum distance, that is A, isn't it? So reciprocal of it, if you are taking, then this value will go up. So it will be now 2 mu sine alpha divided by lambda. Okay, so in this way we can define here, and so at the end we can write if the non-luminous objects are present, then we can find the resolving power of microscope, and that is given as 2 into some refractive index into sine alpha. This is the numerical aperture, and divided by lambda, or it is also written as 2. Sometimes refractive index is given as n, so denoted by n, so that time you have to take n as refractive index, and this is the refractive index of microscope. Okay, this is the first case, we can say case 1. What is that case? If non-luminous objects or dark points are present, then what will be the refractive index? And it is 2 into mu sine alpha upon lambda. Now we will go ahead and we will see the second case, in which we will see the self-luminous points we will see now. So for that case again, the case 2 we will write case 2, and in that we are taking resolving power of microscope. Microscope, fully read microscope with 2 self-luminous point objects. Okay, so now if these 2 points are self-luminous, then what will be this refractive index of microscope, that we are going to. So now here applying Abbe's theory, we can get theory of array disk, array disks. Okay, the path difference, first of all we will write path difference, the path difference okay, that is given by light 1.22 lambda. Okay, so as we know, for just resolved condition, for just resolved condition, we can say here 2a mu sine alpha, okay, that is equals to 1.22 lambda. So now we will equate this. If you are equating this, you can find this a as a we are putting here, and whole thing we are shifting that side. So 1.22 lambda as it is, it will be there, and here you will take 2 mu sine alpha. Okay, so this is the minimum path we can find, but we know the resolving power by definition. Resolving power of microscope, what is that? That is the reciprocal of the aperture. Okay, so whatever you have this value, you are taking upside down 2 mu sine alpha divided by 1.22 lambda. Okay, so if we'll see here, so after dividing this, we can get here this will be now equals to, so RP I can write here, RP is equals to this 2 and this gets cancelled, so here 2 by 0.61 it will be. So this RP becomes now mu sine alpha divided by 0.61 times lambda. Okay, this we can take, or we can, if we simplify this, we'll get here this 1 upon 1 upon 0.61 is 1.64, and into sine mu sine alpha divided by lambda. So this will be the resolving power of microscope. If the two self-luminous point objects are taken, so this is the case 2. So in this way we have here the resolving power of microscope. Okay, in the next video we will learn resolving power of telescope. Thank you.